Welcome to this course on nanostructured materials, synthesis, properties, self-assembly and applications. We are in module 2 and this is the lecture 11 of module 2, and today we start a lecture on lithography, and we will have 2 lectures on lithography. Today we will have the first lecture of lithography, lithography 1, and we will have lithography 2. Earlier we have looked at several other techniques for the synthesis of nanostructured materials involving chemical methods, physical methods, various types of depositions like PVD, CVD, and then spray pyrolysis, VLS methods, several techniques to make nanostructured materials including template methods have been discussed in the earlier lectures of this course. And today we start the first lecture on lithography, and this is the lecture 11 of module 2. The term lithography involves 2 basic parts, litho and graphy. The Greek word lithos means stone and graphia means to write. Hence, the term lithography ideally means a method of producing patterns on a substrate. So, in modern terms we are by lithography we mean we make structures, it may be micron size structures or nano size structures on a substrate which is very well designed, which has a particular pattern, and that is the lithography of today. Originally it started with the meaning as if to write on stone, and hence the term lithography came into existence. Earlier days, several centuries back, the lithography used to be an image which is drawn or etched onto a coating of wax or any oily substance, which is then applied on a plate of a lithographic stone as the medium, which will then transfer the ink onto a blank paper, and hence it produces a particular design on that page using this patterned stone on which you can add ink and then transfer it onto a blank paper. That is how centuries back written material was stored. The history of lithography starts with the person Alois Seinfelder, who is the inventor of lithography, and he has a full text on lithography dated 1819, where he discusses all the possibilities of color printing using this type of lithography, where you have a mold made of wax which is filled with ink, and this pattern on the mold is then transferred on a sheet of paper. This lithography was very useful in the 19th century, and the most important company, the Currier and Ives in 1852, was one of the most important lithographic company of the 19th century, and they produced many prints or called titles, and several thousand copies have been made of individual titles using this type of lithography, where you have a wax mold which transfers an ink onto a sheet of paper or on a leaf or on a cloth, and that was the kind of lithography in the 19th century. The importance of lithography today especially comes from our IC industry. For IC or integrated circuits are the key in all kind of computational devices, whether they are computers or any other electronic devices being used today. And in the manufacture of ICs requires several lithographic steps, and this lithography is cost about 30% of the total cost of manufacturing of that IC, and hence if the cost of IC manufacturing is lowered, that means the cost of lithographic techniques is lowered, ultimately the electronic device, the product will have a much lower cost. So, it is very important to develop techniques, lithographic techniques which can create patterns or here create circuits which can be used in ICs at a very low cost, and hence can bring down the whole cost of the device. Another important thing is the lithography has to go to from one size to ultra miniature size. So, we want to make smaller and smaller devices. To make smaller and smaller devices, you have to make designs or patterns or circuits which have very, very small dimensions, and these devices like the ICs, which we can call as features, have their size has to be reduced. That means, we want low feature size in these devices, and lithographic techniques decide the size of these ultra miniature devices, because your technique, how you are making the patterns, will lead to the dimensions which ultimately form the patterns. Hence, you may have to use certain types of lithography to make certain patterns which are thick of several microns, and if you have to make smaller patterns which are nanometer dimensions, then you may have to use some other type of lithography. So, different types of lithographies exist which are important for different sizes of the patterns or the thicknesses of the patterns which you are going to imprint in your device, and this will restrict the ultimate size of your device. So, there are a large number of types of lithography, and each type of lithography has its advantages and its disadvantages, and of course, the primary thing is to get the pattern of your choice. So, if you need for a particular application a device with certain dimensions, then you have to choose a lithography which will create that kind of dimension, and for that, if the costs are high, you will have to use it. Ultimately, the product will be of course expensive, but depends on your applications, what you want in your device, you have to use that kind of lithography. So, you have photolithography, for example. From the term photolithography, you can understand that it involves light and light induced lithography. So, light can have various wavelengths. So, if you are normally in the visible region, you can call it the solar radiation if you are using, or the optical lithography. If you are using UV light, then it is UV lithography. If you want to use extreme UV, it is called EUV. So, that is even lower wavelengths than UV, and so lower wavelengths means higher energy. So, you are going from the visible region to ultraviolet region to extreme ultraviolet region. So, higher and higher energy of the incident light beam can be used for making different types of lithographic patterns. So, this is photolithography. You can also do E beam or ion beam lithography. That means, you are making patterns or designs on your substrate using an electron beam or using an ion beam. Then you can use X-rays. This is also a form of electromagnetic radiation. So, however, it has very low wavelengths compared to optical or UV radiation. So, X-rays have wavelength in the order of 1 to 2 angstroms, and that is like 0.1 to 0.2 nanometers. So, which is much smaller than the wavelength of the UV or extreme UV radiation. So, X-ray lithography has much lower wavelength, and hence it can achieve certain things which UV and EUV photolithography cannot achieve. So, then you have techniques called the interference lithography. From the term interference, you can understand that there will be a mixing of waves. That means, you may have constructive or destructive interference of two beams, and that can be used to generate patterns, and so that is called interference lithography. Then you have scanning probe techniques, which involve a variety of different there are variations on the scanning probe technique. You have the voltage pulse technique, the CVD technique, the local electrodeposition technique, and the dip pen techniques. These are all scanning probe techniques, like the scanning probe microscopy. Here you are using the scanning probe to make patterns or designs on the substrate, and you have different variations of the scanning probe technique. Then you can have other techniques like the step growth technique, the nano imprint technique, the shadow mask technique, the self assembly technique, the nano templates, and several templates can be used to make patterns, lithographic patterns using these nano templates. Some of them can be made by using die block copolymers or an alumina membrane, or you have channels made in glass. Then you can have membranes which have been made using nuclear radiation. So, these are called nuclear track etched membranes. So, a variety of techniques is available to carry out different types of lithography to maintain patterns, design patterns on substrates, which then can be used for certain devices. We will be discussing some of these lithographic techniques, but not all the techniques, but we will try to cover the important techniques like all the photolithographic techniques, the X-ray lithographic techniques, the interference techniques, and maybe the nano imprint technique. So, these will be discussed in little bit more detail. Now, the basic technique of lithography is that you take a substrate. So, your substrate becomes like the rock or the stone of early days, where people used to want to write something. So, in the modern day we call it the substrate. The substrate can be glass, or it can be silicon, it can be silica. It depends on what you want to do with it. Very important substrate is of course silicon. Then you want to deposit a film on the substrate, and that film on that film you should be able to pattern the film. So, one of the properties of this film is it should be something where you can make some impression, or where you can remove some parts of the film easily, so that it leaves behind a pattern. So, you take a start with a substrate, then deposit a suitable film, then you pattern the film. After you have patterned the film, that means the design is there on the film with the substrate behind it, then you etch this patterned substrate. So, the film is there on the substrate, and the film has been designed or patterned, and when you etch, only the pattern that you made will remain on the substrate. Remaining parts of the film will be removed. That is called etching. So, this etching can be done using different chemicals or acids, and so lithography consists of these 4 basic steps, that you start with a substrate, deposit a film which is suitable for patterning, and after you pattern using some technique, it may be light, it may be electrons or ion beams, or some scanning probe techniques, you pattern the film, then you etch the film such that only the design part of the film remains. The remaining part of the film should be removed and the substrate will have the pattern on top of it. Now, if you consider photolithography, so in photolithography you use light to transfer the pattern from a photo mask to a light sensitive chemical which is called the photoresist or just a resist on the substrate. So, you have a substrate and on that you first have to deposit a film. So, that is the first step in photolithography. You start with a substrate and then you deposit a film. After that you deposit another layer of the photoresist. So, you have one layer of a film and then you have one layer of the photoresist. Then you on top of the photoresist you place a mask. So, this mask has a pattern. So, it has this dark and white zones in the mask, and then when you shine light, the mask is such that wherever it is having some material, it will not allow the light to pass through. However, in this region which is shown as white, the light will go through this and hit the photoresist. So, in this region the photoresist is not having any light falling, only in this region the light will fall on the photoresist. Now, so selectively light is falling in this area and in this area on the photoresist. So, when that happens, this part of the photoresist it gets removed. So, this is a particular type of photoresist which is called a positive photoresist, which we will discuss, where wherever light is falling, that part it gets soluble or it dissolved away and you are left with these gaps. Now, after this step, so you have the substrate, then you have the film and the photoresist is at certain parts of the on top of the deposited film. Now, if you etch or remove this mask, then only you can see this. So, the mask was on top of this, light was passed and it creates this kind of holes. On top of this this film, the mask has been removed and so we etch the mask off and then you can see only the film on top of the substrate and the photoresist is removed at certain parts. Now, the next thing is to remove the you have to etch this exposed part of the deposited film. Now, this exposed part of the deposited film can be removed using certain chemicals and that is called etching, and once you etch, now you have a gap here wherever the film did not have any covering of the photoresist, that part got removed completely. So, you are left with a structure which has got the film and the photoresist on top of it, and then there is nothing here, and then again you have. So, you have generated a pattern of the film, but still now you have this photoresist material on top of those columnar structures of the film. So, next step is you have to remove the resist from top of that. So, you use another set of chemicals to remove these photoresist which is on top of your film. When you remove that, you get the final structures. This is what you wanted, that is what the pattern you wanted. Starting from the film which is here, you designed a pattern where the film exists only in certain parts and wherever you want, and the other parts do not have the film. Of course, as you see that the pattern will depend directly on the mask. So, the mask has to be designed in such a way that ultimately you get a pattern on the film which is the pattern of your design. So, the design of the mask is very important, because ultimately that will be that will be the guide to the ultimate structure that you get, and this structure has the pattern or design which you wanted. So, if you go through the steps, you have a substrate, a film deposited on it, and then a photoresist layer deposited on it, then you have a mask on top, you shine light on the mask, and through the mask wherever the light can go through, it will penetrate and remove the photoresist. The remaining parts, the photoresist will remain, and then you remove first the mask from top of this, and then you remove the when you remove the mask you get this, and then when you remove the photoresist you finally end up with this structure. So, you have made a patterned structure using photolithography. So, the various steps which we already got through, with some more details, is that you have to prepare the surface of the substrate, you have to clean the substrate, then you have to apply the photoresist, then you have to bake it, soft bake, that means little bit temperature, then you have to align the mask. The mask has to sit exactly on top of the film where you want. So, you need what is called a mask aligner, and then you align the mask, and then you expose it to the light, the whatever radiation you are using, and after that you develop, that means you add some chemicals which will remove the mask. So, when you add, after you do the light, you use your light, you etch away the mask which will be on top, and you will get this kind of structure, and then you inspect. If it is fine, then you etch further, remove the resist, and then you get your final structure. So, common factors for photolithography, there are different types of resists. Then what is the thickness of resist you want, because your resist, if it is too thick that light cannot penetrate completely, then you will not have this structure and some resist will remain. So, the thickness of the resist is also important, that depends on what wavelength of light you are using, how much time you are exposing to the light. Then the alignment of the mask, of course, is of ultimate importance, because if you misalign the mask you will not get the structure which you want, because the mask actually guides the final structure. So, the mask alignment, which is done not by hand, but automatically through equipment which is called the mask aligner. So, it is programmed and the mask is goes to the exact position on the resist, and then you do the you expose it to light. Then you have to know the wafer surface. The wafer is basically the substrate here. The substrate is silicon. For IC chips, most of the times we are using silicon. So, the silicon wafer surface has to be very clean, and then you have to bond the resist very carefully. So, the adhesion of the resist, this property of the resist material, whether it adheres to the surface or not properly, is important. Then you have to optimize the energy of the radiation that you are using for exposure of this film. So, the exposure energy is important, the temperature of baking is important, the time that you allow for the development using some chemicals is also important. So, there are several factors which you need to optimize to get a proper pattern using photolithography. Now, the different types of the photoresist, before we go to the different types of photoresist, a typical photoresist consists of the following components. One is the basic resin. It is a material that is a binder for obtaining certain properties of certain chemomechanical properties, certain strengths, certain flexibility and certain chemical resistance for pattern transfer. So, a good resin will have optimal properties which you want, and that is used for different substrates. So, for one resin may not be good for all the substrates. So, you have to optimize the type of resin depending on the substrate, because the adhesion of the resin is important. Then apart from the resin, you need a sensitizer, because you will expose it to light. So, you need a photoactive compound, that means a compound chemical which becomes activated in the presence of light, in the presence of light of the wavelength which you are using. So, this compound should this chemical in the photoresist should get activated at the wavelength of the light that you are planning to use. So, that actually has that we call it as a sensitizer, because it is sensitive to a particular band of energy or particular wavelength of light. Then you need a solvent, and you have to control the properties of the solvent for deposition, like the viscosity, the flow properties, etc., which provide the liquid form for this resin. The resin is in a liquid form when it flows, and then it has to bind. So, to bind you need adhesion promoter. So, together all these four, the resin, sensitizer, solvent and the adhesion promoter make the photoresist. A very important and commercially successful photoresist is the SU8 photoresist, and it is very popular and used extensively in lithographic techniques, and this is a negative epoxy and it works in the near UV radiation. So, near UV there is some wavelength of light where and that wavelength of light it is most active or it is most sensitive. So, SU8 is a negative epoxy near UV photoresist, and we will discuss what is a positive and what is a negative photoresist. So, SU8 is a negative photoresist. So, the type of resist are positive resist and a negative resist. As we said, SU8 is a negative photoresist, but you can have both positive and negative resist. So, what is this positive and negative resist? Now, if you would discuss this first, the positive resist photolithography. So, if you have this is your substrate, and then this is your oxide layer, which is your film. In the previous slides we are talking of a film on a substrate. So, here that film is made of some oxide, and then you have this photoresist on top of that, and then you have this mask. This mask can be some metal and which does not react or is not sensitive to UV light. Now, if the mask is designed in such a way that it allows UV radiation to go through in certain region, this rectangular or square region, and radiation falling on the photoresist in this region will get dissolved, and that is called a positive resist. So, wherever the light is falling, if this resist gets dissolved, those areas that are exposed to light become soluble, then this kind of a resist is called a positive photoresist. And ultimately, you will get a structure like this, where the resist which was here is no more there, because it has been exposed to light, and during that period this part of the photoresist got dissolved, and only this part where no light was coming, because there was a mask on top, still remains. So, the photoresist part which remains is where the mask actually was placed on top of it. So, the resulting pattern based on a positive resist photolithography will look like that if the shape of the mask is like this. Now, if you look at the negative resist photolithography, there is just the opposite. it involves a photoresist where if light falls on that photoresist, that polymerizes. So, that will remain as such, it will polymerize. Wherever light is not there, that can be removed. So, areas exposed to light become polymerized, and then when you add the whole thing to a developing chemical, the region where light was not falling, that resists the that does not resist the chemical, and so it will get dissolved, and areas which were exposed to light, that will resist the chemical. So, earlier areas which were exposed to light became soluble. Now, the areas where light falls becomes polymerized and will remain. The area where light did not fall will actually get dissolved. So, it is just the opposite of the positive resist photolithography. This is the negative resist photolithography, and here the region where the light did not fall, because the mask was designed like this, did not allow light to fall on this region, and since light did not fall on this region, when you put it in the chemical, it removes the photoresist, and the part where light fell, the photoresist polymerized, and now the chemical cannot remove that part, and so the final structure looks like this. So, this is the negative resist photolithography. Now, you can do optical lithography with visible light with ultraviolet radiation, which has wavelengths in the order of 365 to 436 nanometers. Now, when you go from visible to ultraviolet, you are going to smaller wavelengths. As you are going to smaller wavelengths, you can make smaller features. So, if you want to make smaller and smaller features, you go to smaller and smaller wavelengths. So, you can go to UV, which is 365 to this 436 nanometers. If you want still smaller structures, you go to deep UV, that is deep ultraviolet, which is much smaller wavelength and much higher energy, that is 157 nanometers to 250 nanometers. If you want even smaller wavelength, that means even higher energy, you go to extreme UV, which is called EUV, where the wavelength has the values of 11 nanometers to 14 nanometers. And ultimately, if you want to go to even higher energies and much lower wavelengths to obtain very small feature sizes, then you go to X-ray radiation, which has wavelength less than 10 nanometer. It is normally of the order of 1 to 2 nanometers, and so you can make feature sizes much smaller than what you can get using UV or deep UV lithography. So, extreme UV lithography you can use when using UV lithography, you are at the limit of the minimum feature size. That means, you cannot make designs or features smaller than the UV radiation, but you need them. Then you go to EUV, which is the extreme UV, and since very few materials transmit extreme UV light, so you have to use reflective instead of transmissive optics, because most of the materials they reflect the light instead of transmitting the light, and so your optics have to be changed. The masks for used for lithography using such extreme UV radiation uses heavy metals for forming the mask patterns, and because those absorb the EUV radiation. So, heavy metals may be gold or platinum, they can be used for forming masks which will absorb the extreme UV light, and wherever in that pattern there is a hole or there is a gap, the light can penetrate and will affect the film underneath the mask, and hence your pattern will be generated. Now, the resolution of such a photolithographic process is limited mainly by the diffraction of the light used for exposure. So, to reduce the diffraction and achieve the highest resolution, you can use shorter wavelengths as we discussed. You can use deep UV, ultra extreme UV, and you can use different sources for them. For example, you can use an excimer laser which uses radiation of the wavelength of 193 nanometers. You can use mercury vapor lamp or xenon lamp. So, you can use shorter wavelength to avoid the resolution which is limited by diffraction. Of course, you are going down below the UV limit. The other thing is you can choose high numerical aperture lenses to project the light. So, higher the numerical aperture, your resolution, that means your ability to see 2 points close together will improve. So, you can come down to much smaller dimensions between 2 points and resolve them if you use a very high numerical aperture. So, that will become clear if you look at this equation, where the resolution you want very small numbers here. So, Lm, which is your resolution, should be very small. Now, this can be very small if either lambda is very small, which is the wavelength, that means you keep decreasing the wavelength. That is why you go from UV to deep UV to extreme UV, and then you go to X-rays. But in the other thing that you can do is you can increase the numerical aperture Na here. So, if you have very high numerical aperture, then also you will have a very small number for the resolution. That means your resolution is very good. Now, this is typical for any these are typical optics for any microscope or optical either optical microscope or electron microscope, where you have your source which may be an optical beam, light rays, or it can be an electron beam, and then you have lenses to focus the beam, and when it is focused, there is this angle which is actually should be discussed as a solid angle, but we are now looking at half of that angle, and that angle theta, if you take the sine of that angle of the half angle theta, that multiplied by n, which is the refractive index, you calculate the numerical aperture. So, the numerical aperture you want is a very large number, and this numerical aperture will be large if you have a very large theta value or very large n value, right, because you will have the maximum value sin theta equal to 1 when theta is equal to 90 degrees. But of course, you cannot do that. So, this theta you can vary to increase the aperture to a certain extent, and you can change the refractive index by changing n. So, you can control the numerical aperture and you can get a better resolution if you have a high numerical aperture. So, the wavelength of light and the numerical aperture both control the resolution, and you want a low wavelength and high numerical aperture to achieve the best resolution. Now, so one thing is, which I already said, that you need for better resolution in photolithography, you need a large numerical aperture and short wavelength, and short wavelength you can go to deep UV, extreme UV, or even X-rays. Now, if you want to go to X-rays, then we come into the term what is called X-ray lithography. So, you are going to use X-rays as your source of radiation to make patterns on the films, and this methodology, the X-ray lithographic technique, allows you to have very high or super high resolution pattern transfer. So, when you are transferring the pattern of very high resolution, then this technique is very important. There are other techniques like the UV lithography etcetera, have a limit to what kind of resolution of pattern can be transferred onto the film. Now, but X-ray lithography has technical hurdles, and most time you need synchrotron X-rays. So, synchrotrons are not available very everywhere, you cannot have synchrotrons in every laboratory. So, synchrotrons need to be further developed, and so it is expensive, and you need these synchrotrons because they will give you collimated X-rays, and those are normally used for X-ray lithography. Now, that makes this X-ray lithographic technique a little expensive, and so it has to be used for very high end product design. So, X-ray lithography is similar to photolithography, except that you are using X-ray radiation instead of visible light or ultraviolet light, and you have to keep a gap between the silicon wafer or your substrate and the mask. In the earlier techniques, you used to put the mask right on top of the film, which was on top of the substrate. But in X-ray lithography, there is a gap between the substrate or the film on top of the substrate and the mask, and then you have to have X-ray resists, that means certain materials which will not allow X-rays to pass, and X-ray masks are always thinner. So, there are certain differences between X-ray lithographic techniques and normal optical lithographic techniques. So, this is a typical diagram to show you a X-ray lithographic process. So, you have your substrate, and on top of the substrate you have you will have your image of the pattern which you have on the mask. So, this mask, which is kept little bit away from the substrate, there is a gap between the mask and the substrate, and the mask is of two parts. The mask is made up of an X-ray absorber which is patterned on this mask. So, these are X-ray absorbers, and in between there is these are gaps where the X-ray is not absorbed. So, you have an X-ray absorber, and there is a material, a film which is transparent to X-rays. So, wherever the material is transparent to X-rays and there is no absorber behind it, then the X-rays will pass on through the this material and then hit the film. So, this film on the substrate is typically a polymer like PMMA we call, it is used very commonly in many photoresists. So, what you have is your X-rays falling on the mask, and the mask is made up of two parts. You have an X-ray absorber which will absorb the X-ray if the X-ray comes in its path, and there is the resist which is transparent to X-rays, and you get feature on the PMMA, which is the PMMA is where you will get the final image. So, you transfer the X-ray whatever the pattern on the mask on top of the PMMA using these X-rays. Now, the materials which are used for X-ray absorption are typically metals with high atomic numbers like gold, or compounds of tantalum or tungsten which are also of high atomic masses, and the layer which is transparent to X-rays in the mask this layer is typically silicon carbide or diamond, and as we already discussed, the film on which the image will be formed is typically a polymer which is PMMA. And so, whatever be the design here, that design is recreated on the film, and this is called the latent image. So, you will see that wherever there is a gap here, the film here, this film of PMMA has been removed by the X-ray, but wherever you have this absorber, that part of the film is intact. So, you can make a pattern using X-rays. You use a visible light and some alignment optics to align your mask, and you see such that you have the right positioning of the X-ray absorbers to create the right pattern on the PMMA. So, this is a typical X-ray lithographic technique where you are using X-rays. There are a couple of differences with the earlier techniques. The mask is kept away from the film of the polymer, and there is a gap. This is an important thing, and then the materials that you use are different. You need to make the mask in such a way that you have some X-ray absorbing materials on the mask, and these X-ray absorbing materials are made up of either gold or some compounds of tantalum or tungsten. So, this is the X-ray lithographic technique, and with this technique you can make very fine features, because the wavelength of X-rays is very small. It is 0.1 to 0.2 nanometers, and it resolves the diffraction problems of normal UV radiation. So, in photolithography using UV, when we come across the problem of the diffraction limit, then if you use the X-ray techniques, it resolves that diffraction limit, because you can go to shorter and shorter wavelengths like 0.1 to 10 nanometers, and hence you can generate much smaller features using X-ray lithographic technique. Now, there are certain disadvantages too of X-ray techniques. One is, I already mentioned, that it may be expensive. You may have to use synchrotron sources, then you have to use thin X-ray masks, and those are expensive. Then there can be deformation in the polymeric film, and there can be vibrations, and this process is also time consuming. So, these are some disadvantages. Of course, if you want to have very precise and small features, then you have to go for X-ray lithography. Now, then we move on to what is called interference lithography. The term interference, as commonly studied in physics, as you know, you have two different waves, and they are interfering to create either constructive and destructive regions. So, somewhere the amplitude of the resultant radiation or the resultant wave will become higher, and some places it will become lower. So, this technique, interference lithography, where you is the preferred method, where you want large scale pattern formation, and if you want where the periodic or quasi periodic patterns are coherent over large areas. So, this is a very good technique for making such large area patterns. So, here you can see that you have a silicon substrate on which you have an anti reflection coating, and then you have this photoresist on you can have a negative photoresist or a positive photoresist, and accordingly you can get the patterns on top of them. So, the basic mechanism of this interference lithography is you make an interference pattern between two light beams. Here if you choose ultraviolet or UV light, then you have two beams of UV light. So, this is one beam and this is another beam, and they are kind of tilted at an angle theta, So, they will interfere, and when they interfere they will generate this pattern, and if you look at the variation of their amplitude, then you will see a periodic variation of this amplitude, which is related to the wavelength and of course, the angle of the at which the two radiations are meeting. So, you normally use a UV laser which is split, expanded and superimposed to form the interference pattern. Now, this technique is very good because you do not need a mask and it is not a scanning process. Now, if you use X-rays, that is, you pass two beams of X-rays instead of UV, then you get what is called X-ray interference lithography. Now, if you use X-ray interference, then you get high resolution. You can go to sub 5 nanometer region, and you can get periodic structures of less than 5 nanometers. You have high throughput, that means you can make many nanostructures very quickly. There are no charging problems in this technique, and you can use other photoresist processes in addition to direct modification of films, just like these kind of SAMs, which are called self assembled monolayers, and the mask fabrication is much easy compared to other lithographic techniques. So, X-ray interference lithography is a very advanced form of lithography, where you are using two X-ray beams to interfere and creating periodic patterns, and these periodic patterns are at a level of less than 5 nanometers periodicity, and using this you can generate very large scale periodicities. So, the X-ray interference lithography is shown here. You have X-ray from synchrotron going through a pinhole, and this synchrotron light is then diffracted at a grating, and that grating is basically a mask, and the pattern on this mask or the will result in the ultimate image that you want. So, you have this substrate, and this substrate is coated with a resist. On top of the substrate you have the resist, and when the X-ray after interfering here, it creates a pattern here, then that pattern will be etched on the substrate. So, you are using X-rays going through a mask which has a particular pattern, and then diffraction is occurring, and you are getting a periodic structure based on the interference of the two beams, which is the two beams are being generated by this grating, and you get a structure of your choice by the design which you made in the mask. And this is the way that you generate X-ray interference lithography based on two X-ray beams which are interfering with each other. The advantages of interference lithography is that it is a one step process. It is not that you have to repeat steps after steps, and it allows for processing of a complete substrate with one single exposure. So, you can use a very large pattern can be generated using a single exposure. Of course, if you have very complicated pattern, then you have to do several exposures. It is possible to make very small sub-micrometer structured surfaces on area which are more than 1 square meter in size. So, it is very effective for large scale structures. It is time and cost effective compared to many other patterning technologies. So, these are the advantages of X-ray interference lithography. With that, we come to the end of today's lecture, this lecture 11 of module 2, and I thank you all for your patience, and we meet again for the 12th lecture on which will be the second lecture on lithography. Thank you very much.